Hello, college math topics. We're in the class notes under 3.3 solving systems of equations. So this is in class notes, and you're going to take notes along with the video. If you need to pause it, feel free to do so. So to begin, we're going to continue to solve systems of equations, but we've done guess and check when we were kind of like playing with those cards with the like round tables and rectangular tables. We needed 25 total with 190 seats, and then we kind of guessed and checked till we find the right combination. And then we were able to write systems and use graphing technology to find the intersection. And then we did it algebraically by the substitution method. And now I'm going to also show you this elimination method, which will be familiar to you. Sometimes elimination is the easiest way to go. Sometimes substitution might be easier. But I just want to show you this last method of solving systems. So the objective is to solve certain types of systems with elimination and determine when systems have no solutions or infinite solutions, which is, again, somewhat review. So what is elimination? So elimination is when we add or subtract equivalent expressions on each side of an equation to eliminate a variable. So if you add or subtract some equivalent expressions, so expressions that have the same value, as long as you do it to both sides, again, that creates a new equivalent equation. This is similar to when we do things like adding 5 to both sides. So consider the system below. We have two equations, two unknowns. Now, right here, if we subtract the x, if we subtract these two equations from each other, the x's will cancel. And that's always the goal here, is to eliminate a variable so that we can just write an equation with one variable. So in the problem here, we're going to have to subtract the x on both sides. Excuse me, not the x on both sides, this expression on both sides. So what I'm doing here is I'm going to subtract this bottom equation from the top equation. So this bottom equation, if I subtract it, this becomes x minus x, so that's just going to cancel and become 0. Now when I do 4 minus negative 3, that double negative is going to make that really 4 plus 3, and it's going to become 7y. And then 11 minus negative 3 is really going to become 11 plus 3 because of the double negative, and that becomes 14. So what we just did is we subtracted the bottom equation from the top equation, and that's okay because it's like subtracting 3 on both sides. If I subtract 3 from this side, I got to subtract 3 from that side, and subtracting 3 is equivalent to subtracting x minus 3y because they're equivalent expressions. So in the scenario, I have 7y equals 14, and from here we're pretty good. Just divide both sides by 7, and then I just know that 14 divided by 7 is 2. So one little trick that I do when I'm subtracting equations from each other is I know all the signs are going to change. So I'll make that a negative, I'll make that a plus, and that a plus, because in my mind, now I just combine like terms. 4 and 3 gives me 7, 11 and 3 gives me 14, and x minus x gives me 0. So when you're subtracting, you can just change all the signs. So, so now we have an equation that we can solve. So down here, it's the same system. The strategy in general for solving these problems is manipulate the equation so that variables will cancel out. So sometimes we have to do some manipulating, but we always want a variable to cancel when we do the add or subtraction. Then we add or subtract, and then solve the new equation. And we just did that, but now we need to go back and find the other value. So we knew y was 2 from above. So right when we subtracted these, we got 7y equals 14, and then y equals 2. Now that I know y is 2, we can pick either of these equations to plug y equals 2 in to solve. So I'm going to pick the top one. The top one is x plus 4y equals 11, but I'm not going to put a y here. Instead, I'm going to substitute the value 2 into the equation. Now that I know that y is 2, I have an equation with just x. So this becomes x plus 8 equals 11. Subtract 8 on both sides. And then we find the other value, x equals 3. So the point 3 comma 2 is where the lines would intersect, but that is the value of x and y that solve that system. Okay. So now I'm going to go to this next example here, and I'm going to kind of highlight this again. Sometimes you need to manipulate the equation so that the variables will cancel out. So in this situation here, If I add or subtract them, the x's won't cancel out because they don't match, and the y's won't cancel out because they don't match. But what I can do to both sides of this bottom equation here is multiply both sides of it by anything I want other than 0. And I'm going to choose to multiply both sides by 2. Now that might seem random, but when I do that, that's going to give me a negative 2x, a 4y, and a 10. So that's when I multiply by 2. This first equation, if I leave it alone, it's still the same equation. But now that I multiplied it by 2, see what happens here with the x's? I get them to match, and when I add these equations to each other, the 2x's minus 2x is going to cancel out. Then negative 5y plus 4y is going to give me negative 1y, and negative 11 plus 10 is negative 1. So then now I have an equation with one variable. We can just divide both sides by negative 1 and get that y equals 1. Okay, so now that I have y, we're going to x. Doesn't matter which equation we use, so let's just use the first one. 2x minus 5 times y equals a negative 11, so I copy it down, but I replace y with 1. 5 times 1 is 5, so this just becomes 2x minus 5 equals negative 11. And then I'm going to add 5 to both sides to get rid of the minus 5. So I have 2x equals negative 6, and then divide both sides by 2. Oop, not 3. And that's going to give me x equals negative 3. So now we have y and we have x. Negative 3, 1 would be the intersection of those lines. So that's just using elimination to solve systems or equations. It's a little bit different than substitution. It can be easier in some cases. In some cases, substitution might be easier. The second objective for today is when there's infinite or no solutions. So that happens when the variables cancel out. So when both variables, I'm going to say get eliminated. When there's no variables left, then the system will either have no solutions or infinite solutions. So if you get a situation where the remaining equation is true, then there's infinite solutions. Graphically, if we were to graph one line, suppose one equation looked like that. For a system to have infinite solutions, then the other equation is just going to be right on top of it. They're going to be the same line. So graphically, that's what it looks like. It says when if the remaining equation is true, there's infinite solutions. So if at some point the x's and y's both cancel out and you get something like 6 equals 6, if that's true, which it is, then that means there's infinite solutions. If you get something that's false, like 6 equals 7, when the variables cancel out and you get a false statement, then there is no solution. Now graphically, that's when the graphs do not ever intersect. So if one graph looks like this, then the other graph might look like this. So if they're parallel to each other, there is no solution. That's what it looks like graphically. And even if the functions aren't linear functions, you could still have a situation of no solution. So if I had a graph that looked like a parabola, and I had, suppose this line right here, there is no solution to that system if they never intersect. So they could be parallel lines, but even if the graphs aren't parallel, as long as they don't intersect, there's no solution. So right here, we're going to see that happen. Solve the system of equations, and I have them where the x's and y's are kind of set up on top of each other. I'd like to try elimination here. So I know if I multiply this bottom equation by 2, this 2 will become a 4, and then I'll be able to cancel out with that 4. So I'm going to double both sides of the equation. So that's going to give me a 4x minus 3y equals 4 times 3 is 8. And this top one here, I'm just going to recopy it down. Now, for the x's to cancel, I'm going to have to subtract. So remember, when I subtract, all that does is changes all the signs. So that's going to become a minus, that's going to become a plus, that's going to become a minus. 4x minus 4x becomes 0. Negative 3y plus 3y cancels out as well. That becomes 0. And 8 minus 8 becomes 0. So in this case, the x's and y's both canceled out. Now the question is it a true or false statement? 0 equals 0 is true. So that means there's infinite solutions. Okay? So That's it. What I'd like you guys to do then is go under the class work section, and you're going to work on the systems of equations 3.3 practice. Oh, wait, hold on. I remember there's one more question for you guys to look at down here. There it is. One more question. Okay. In the system equations below, k is a constant, so it's just some number. What is the value of k so that it has no solution? So we want to create a system of equations such that there is no solution to it. So for there to be no solution to infinite solutions, what we need is the variables to cancel out. So if I want to get the y's to cancel out, I would multiply the bottom equation by 4, because the 4 times the 2 will give me an 8, and then I can cancel out the y's. And then based on that, I'll figure out what k needs to be so that it matches up with the 5. So if I multiply that by 4, I'm going to get 20x minus 8y equals 14. And I still have kx minus 8y equals 30. So again, I want there to be no solution here. If I were to subtract these, the 8y's will cancel out. But I also want these to cancel out too. So the only way for these to cancel out is if k is 20, because then they'll cancel out when we subtract. So that's the value that'll create a system with no solution. Just kind of want to show you what it looks like on Desmos. 5x minus 2y. It's 14. And kx minus 8y equals 30. Ooh, 30. Alright, so if I were to make this k 20, I should create parallel lines that'll never intersect, which is what I wanted. Additionally, if you didn't want to do it that way, you can use this slider feature, and you can kind of move this around until it's kind of like where you want it to be. Now it only goes up to 10. So if I made that 10 go up to, like, let's just go up to 25. Now I can make this k a little bit bigger. This slider allows you to play with different values of k and see what happens. And we figured out that 20 is the value that makes them parallel. So you could also use the slider feature there. Anyways, that's it for the video. If you liked it and want to hear more, make sure to smash the like button, ring the bell for notifications, and leave a comment if you have any questions. It really helps out the channel.